All right, we'll get started. Welcome everyone. I hope everyone has been having a good week so far. Probably one of the toughest times we're living in, but I hope all of you are coping well. Before we get started, any questions about the exam? You have an exam which starts tomorrow. So it starts tomorrow, 6 a.m. California time. I mean, that's when the problems will be made available, and you'll have 24 hours to turn them in. Uh, Before I take questions, just want to give you a piece of advice. So we have 24 hours to turn it in. My advice is not to wait till the last hour to turn it in. You'll not need 24 hours to finish the exam. So make sure you turn in your exam well before time. Uh, we are going to be slightly strict about this time because it's an exam. So we will not encourage email submissions. We are not going to take submissions if you turn them in after the deadline. Okay. So don't wait till the last minute because you'll have internet issues. The server might go down. If all of you or if some of you start doing the upload at the same time, it might just not go through. So just don't wait till the last hour. Okay. At least do it an hour before, at least. Okay. Before we get started, any questions about the exam? Any questions about the class in general, policies? So I've not graded your quiz and your homeworks, but the solutions are available on Blackboard. I'll be grading them at the end of this week. No questions involving R. So there's a question about asking if there will be any question about R. So you don't have to code in R. I mean, you don't have to use R. That said, that you can use R as a calculator if you want, if you don't have a calculator, but you will not be asked any questions on R particularly. Any other questions? Yes, very similar to the, so will the exam be similar to the first exam in format? So it's identical actually. The format remains pretty much the same. So you have around set of 5 questions, 5 or 6, I think 5 questions, and they have subparts. Some subparts are related, some subparts are independent. So make sure you read the questions beforehand, before answering all of them. If for some reason you have to make any assumption about anything, then make sure you also write down your assumption. Okay. The exam is meant so that there should not be any ambiguity. But if you find something ambiguous, let us know. But I don't believe there's any ambiguity in the exam. Okay. All right. So we'll get started with our discussion for today. I'll have the way this discussion is designed is we have some review problems. We might not have time to go over all of them. So I'll just quickly give answers to some of them. But the solutions are going to be uploaded. I mean, they're going to be available just once we end this session. So you'll have solutions to everything. Okay. All right. So I'm going to share my screen. I'm going to turn off my video. Okay. So while I'm writing, if there are any questions, either raise your hand or unmute yourself and you can ask directly as well. Okay. All right. Okay. So this discussion will carry on from what we did in the last time. So what we did last time, we left a problem incomplete, which was essentially on Wilson adjusted proportions. All of you have already seen it because it was there in your quiz. It was there part of your homework, but we'll just do it for the sake of completion. Okay. And this problem comes from this idea of doing the poll for a precedent and asking how many people are going to vote for a particular person. So in the first problem, you're asked what proportion, what is the estimate of the two proportion? So the idea would be, we've already given that 6 out of 37 people vote for a particular person and 1,000 is what is your total. However, the problem with this estimate is you cannot estimate the confidence intervals, right? So the confidence interval for this estimate is not known. What's, however, known is we can force this interval, we can force this proportion towards a value of 0.5. And the way we do this is by adding 2 on the numerator and adding 4 in the denominator. So essentially, you're adding a value of half in some sense. And this proportion, if you calculate the value, that's 0.636. The reason we like this Wilson adjusted proportion is because the confidence interval for Wilson adjusted proportion is characterized or is known, which is not the case with your just vanilla proportions. Okay, so that's fine. And this is a simple problem. The next question is 95% confidence interval for this proportion. Okay, so it's essentially asking us that how can you actually really trust? In some sense, it's asking how trustworthy is this particular proportion. So we already know by this time this is pretty standard by now. So we call this p tilde, and p tilde plus minus 1.96 times the standard error of p tilde is what this value is. The standard error itself is given by a simple formula, p minus 1 p by n plus 4. Okay, so you've already seen most part of this. So you can imagine this is a Bernoulli trial with a success of p, or a probability of the success being p, and hence the variance of this particular value or random variable is given by p times 1 minus p. You're talking about standard deviation, and particularly you're talking about standard errors. Hence, you take a square root and divide it by the total sample size. And the important thing that here is this is n plus 4 and not n. Okay. So we plug in the values here, and if you do so, the value that you get is 0.015. Okay. So the confidence interval, essentially, if you plug in the values there, because you all have access to all the values, is going to be 6066 to 0.6654. Okay, so that was again fair and simple. We move on to problem 3, and the problem 3 is asking us that now you're desired to have a standard error of no greater than 0.01. So that's like your low bound. How many people should you be surveying? So you want the standard error of the estimate to be as small as 0.01. How many people should you be surveying? So that again is simple. We simply plug in the formula first. So we know p hat is 0.636, and we want to estimate the value of n hat, right? And the way this is done is you simply take it on the other side and square both sides. Okay, and if you plug in the values, this comes around to be 2315.04, which essentially now means that this is going to be greater than at least 2312, because n is a number. So if you simply do a subtraction of n 4 from both sides, you get 2311.04. And that essentially means that since we are talking about numbers, this number will be at least 2312. I'll do the part D here. So in part D, you're asked, what should be the value of the estimate? What should be the value of the number of people that you're going to survey if the estimate of the proportion was not available? Okay, and you still require the standard error to be less than 0.1. So how do we solve that? Okay, so the formula still remains the same. So we still want the standard error to be greater than p hat, the standard, which is the standard formula for your standard error. But what's not known is what's p hat, and what's also not known is what's n. This is something which we want to estimate. And we want to be able to, when you're given problems like this, you essentially think about the worst case scenario. So what would happen in the worst case scenario? So we want something to be smaller than 0.01. Okay, so we have a numerator and a denominator here. So what's the worst case possibility? So the worst case possibility is that the numerator is a very large number. Okay, so if the numerator is very large, then this proportion essentially is going to be a very large value. Okay, and it still needs to be less than 0.01. So we will design it so that even in the worst case scenario, when numerator is very large, then we get a value which is less than 0.01. So how do we do that? So in order to do that, we look at how would the distribution, or how would the graph of p times 1 minus p would look like. So P is a value between 0 and 1. It's a proportion. So if you plot this on, if you plot on the y-axis, the value of P times 1 minus P or square root of it, doesn't matter. And on the x-axis, you plot the values of P hat. Then you'll notice that at a value of 0.5, you get the maximum value. Okay. So this is a worst case possibility. The worst case possibility of being a very large value, this value is essentially 0.5 times 0.5, square root of that. And that's the worst case possibility of this happening. Okay. So you plug in that particular value there, and what you'll get is that n is greater than, sorry, n plus 4 is greater than or equal to 2500. What that means is n is at least 22496. Okay. Okay. Any questions? It's fairly straightforward. Okay. So move on to the second problem, and the second problem is essentially giving you a flavor of how to test for associations. You've already seen one flavor of this in your class, or when you were talking about the Chinese death problem. So this is derived from a similar problem, and now you're looking at, is there any association between the birth month of famous people versus the month in which they happen to die? So the supposition is this, or the assumption is this, that, or the hypothesis is this, that a famous person would probably end up dying much after celebrating their birthday. If they're dying in a particular year, if it's known that they're dying in a particular year, then we expect that since there is a they look forward to their birthdays, then there's a high chance that they'll end up dying after their birthdays. So the data that's given here is, okay, let's see, question. Okay, so there's a question about, okay, sorry. So let me go back to problem 1D. There's a question about how did I reach there? Okay, so let me take back a step and see what we were trying to do. So what we were given was, we were given that you want to design a study. So you want to essentially design a study so that the standard error of this proportion is less than 0.01. And the way we are going to do that is, we are in some sense constrained because we do not know what the value of this proportion is. If this value was known, then this is a very simple problem because that's what we did in part C. But the reason this is a slightly different problem is because in this problem, we do not know what p hat or p tilde is, and we do not even know what n is. And that's something which we want to estimate. So how do we do that? So the way to do that is to design. So we want 0.01 to be the maximum possible value of this proportion. Let me use different colors. So we want this value to be, if we design this value to be the worst possible scenario. Okay, so how do we design it for the worst possible scenario? Even in the worst possible scenario, the blue box here should still be less than 0.01. Okay, so how can we make how can we design it for the worst possible scenario? In the worst possible scenario, the only way to make this a very large number, if we assume that n is known, is to make p times 1 minus p as large. Okay, is that clear? Why? So the reason we're making it as large as possible is because that's the only way we are, in a sense, we are designing for the worst case scenario, and that's the only scenario in which we can actually constrain. If we constrain our n to be constant, then that's the only scenario which can make this number to go very large. So if we want to make p minus 1 minus p as large as possible, how do we do that, right? Because we don't really know what p hat is. But what we know is, if we actually plot it, then your p times 1 minus p is going to get a maximum value at p equal to 0.5. Okay, you can actually literally draw this, but even if you don't want to draw, you can trust me on this, that if you plot the value of this, and there's one quick way to see this, right? So at a value of 0, this value is 0, and a value of 1, this value is 1. Sorry, this value is 0 again. Okay, and somewhere in between it takes the maximum value. So we plug in p hat equal to 0.5. Okay, so p hat equal to 0.5 makes the numerator largest, and hence we just plug in the values there. So if we plug in the values there, then p hat times 1 minus p hat is 1 by 4, which is what I'm using here. Okay, is that clear? Okay, cool. All right, so move ahead to go back to problem 2. So in problem, you're given 12 months, and you're given these months are essentially, okay, so the numerator. Okay, let me make sure I clarify things. Okay, so maybe I'm not writing it properly. So I'm not doing anything. Complicated here. So what I'm doing here is simply. So let's do it step by step, just because it's creating confusion. Okay, so let me take the square of both sides. So that's p times 1 minus p hat by n plus 4, which means n plus 4 is greater than or equal to p times 1 minus p hat by 0.01 square. You substitute p hat equal to 0.5. You get n plus 4 greater than or equal to 25. So this becomes 1 by 4. And this is 0.01 square, okay, which essentially means n is greater than 2496. Okay, so this is 1 by 4, not 114. Okay, if that was confusing. Okay, so again, back to this problem. We have 12 months and we want to be able to test, and the problem asks us to state the null hypothesis and check if the data is consistent with the null. Okay, so what's a null? So a null is there's no association between the birth and death months. Okay, what in essence this means is we do not expect them to be associated in any way to each other. An alternate is, in this case, there is some association, and we'll leave it there. The sum association can actually go in either directions, but we'll talk about it in the second part. So how do we test this? So the moment you see anything which has this association term mentioned and it's done in a categorical sense, so these are values, or these are what's called levels of categorical variable, right? So what are levels? So the birth month itself is actually, or the death month itself is actually a categorical variable, and it has 12 possible values. Right? You can either, so somebody can either die 6 months before, or 5 months before, or during their birth month, which is essentially this value, or they can die to something like 5 months after their birth month. So there are 12 possible values, and you want to be able to test if there is any association between these 12 values and the birth month itself, right? So in essence, we're trying to test if the birth month, if the death itself is dependent in some sense into what month the person ends up dying. So we have a total of 121 deaths happening over 12 months. So by all expectation, we can say that there's no association. When we state that, what that essentially means is we expect on months, we expect a total of 125 per death. So we, on average, in every month, we expect around 0.4 deaths. Okay. However, is Here. Okay. So we have an issue. We have an expectation in terms of these many number of deaths happening. So the way to test this is by what's called a chi-square test. And chi-square statistic is the choice of statistic when you're testing for association tests. Okay. There are other tests for association as well, but this is one of the tests that we are going to focus on. Okay. So this statistic is very simple. What it says is you measure how much difference is there between the observed and the expected. And all we care about in this case is a positive deviation. So it's this value is always going to be positive. So you take the square of that and you essentially then divide it by the expected value. So in some sense, you are measuring how different is the observed from the expected, having adjusted for the scale of the expected value. Okay. So if we do this exercise for this particular problem, so we already have this expectation that in every month we expect around 104.25 deaths. So if we calculate the statistic associated with that, okay, and you do it for all the 12 values here, your your chi-square statistic comes around to be 17.192. The number of degrees of freedom for this is essentially n minus 1, which is essentially 12 minus 1. And the way to remember this is once you're given these total number of deaths, which is 1251, and if I told you that you have, if I gave you only 11 categories or 11 values of these 11 numbers, then you should in principle be able to figure out what the 12th value is, right? Because the sum is constrained. And hence the number of degrees of freedom is one less than the number of total data points that you have. Okay, so we have the degrees of freedom, we have the test statistic. Now what we do is we go to the chi-square table, which is given at the end of your book, so just table 9. Okay, so we go for the 11th column and we start looking for 17.192. And you'll see that this value happens to be somewhere between these two values. Okay. So before you do any p-value calculation, one thing that you should really keep in mind is to read what the table is telling you. Okay. And these are by default non-directional. Okay. So our p-value is constrained between 0.2 and 0.1. Okay. Most of the chi-square tests are most of them are generally non-directional, not always, but most of them. At least if there are more than 2 categories, then we generally, I mean, there's no known possible test for testing for directions if there are more than 2 levels of a category. Okay, we are working with 12 levels, so we'll always be working with non-directional version of it. Okay, so a p-value is between 0.2 and 0.1, and hence at alpha equal to 0.05 or even alpha equal to 0.1, we fail to reject the null. Okay. So if you note down, if you explicitly write down what your null is, you don't have to expand on that, right? So you can just leave it there that we fail to reject the null, where our null essentially was that there is no association between the birth and the death. Okay. Okay, so that was one way of looking at things. But if you really think about this particular problem, what is it that we are really interested in? So we are really interested in testing whether the death happens before or after the birth month. Okay, because that's a more interesting statistic that we really want to test. How do we do that? Okay, so there's one other way of looking at this problem, and that other way is to actually cluster this information. So you can cluster this information by looking at whether the death happens before the birth month or it happens after or during the birth month. Okay. So we are still looking at the same number of deaths. We are still looking at the same data, but we are looking at, rather than looking at an individual month level, we are now looking at whether the death happens before the birth month or during and after the birth month. Okay. And now we are asked that if you look at these clusters of months before and after the birth month, how would the null hypothesis change? Okay. So in part B, the null hypothesis is slightly different from what we looked at part A. And this null hypothesis is there is there's no association between the let's see how to write this. So it's probably not the right way to, so okay. Between the before and after that. Okay. Okay, so in some sense, what I'm trying to say is that the association between the birth month and the cluster month in which the death seems to happen are independent. Okay, so what does it actually mean? That the birth month is in some sense, there is no association between the birth month and which of these clusters the death seems to happen. So in some sense, it's kind of equally likely that the death will happen in either of these clusters. Okay. The alternate, on the other hand, is, so what is going to be the alternate for this case? So it's directional. So it's going to be slightly different now, right? So we expect the number of deaths in cluster 1, which is essentially before the birth month, to be smaller. Okay, so we expect that because of the expectation that the birthday is going to be celebrated in a particular month, a lesser number of these celebrities will end up dying before getting to see their birthday being celebrated. Okay, so how do we test this? So the test association is, there is still an association being tested. There is still, the association in this case is different, and the difference arises because now we are looking at just before and after events. Okay, there's just two events, or there are just two levels. Earlier in this problem, there were 12 levels because we were individually checking for association between one particular birth month and the remaining 11 months. But right now, we're just looking at before and after events. And as such, the expectation that we have in either of these clusters is the same. However, rather than dividing by 12, now I'm dividing by 2 because we have just two levels. Okay. So on an average, you expect around 625. Let's see, 0.25. Is that right? No, I think it should be 625.5. Okay, so we expect on an average 625.5 deaths to be happening, right? And if we calculate the test statistic associated with this, then we get, so this time there are just two values. So we obtain a test statistic, which is, I think, around 15.38. Okay. And the degrees of freedom are now just 1. So if we test for the p-value, so we go again to table 9. The degrees of freedom are 1. Our test statistic is around 15.38. So it's going to be beyond this particular value, right? So 15.38 will happen here. Now, again, this is non-directional. So P is definitely lesser than 0.001. But this is what we are testing for is one directional, and hence we divide the p-value by 2. Okay. So final p-value is less than this particular value. Okay, so based on this, we find at alpha equal to 0.05, we can reject the null. Okay, and this might sound a bit surprising because in the previous problem, we failed to reject, right? We were still looking at the same problem. In the previous problem, we could not find, so let's do this division. So in this problem, we failed to reject the null, right? This is part A. So in part A, we failed to reject, whereas in part B, we are still looking at the same data, but now we are able to reject. So why this discrepancy, or why this difference of conclusions? Okay. And in order to be able to figure out why we are doing this is because the hypotheses in these two problems are completely different, right? So the hypothesis in part B is more specific. And what does that mean? So it's more specific. Sorry, part A is actually more specific. And it's more directed towards, okay, let's write it unambiguously, is directed towards testing association between different months individually. Okay. Whereas in the second problem, we are essentially looking at just before and after events. So we have a question. Oh, sorry. Yeah, sorry, I missed that. Sorry. Yeah, good point. There's an error here. Needs to be divided. Sorry, missed that out. Okay, so this value is still the same because I calculated beforehand, but the value is different. But the calculation was, I missed out the denominator earlier. Okay, so the reason which this is different is because of the change in hypothesis itself. Okay, and to think of this in a real life setting, you will always choose your hypothesis before actually doing the test. It will not happen that you will do these two sorts of tests and then decide that I'm going to, since the second one is significant, I'm going to go ahead with that. Okay, so one thing that you need to realize from this problem is to choose a hypothesis which is something which closely resembles the problem. The problem here was being able to test whether we have whether more number of, more interesting hypothesis is to really test if they happen to die before or after. Okay, whether or not they happen to die in a particular month, or how is it associated with the death month, is a less interesting hypothesis to test. Okay. Okay. All right, so we'll move on to problem 3, which essentially is a generalized version of a chi-square test. And these are called, so this, when you see the data in this form, these are called contingency tables. So these values here are two levels of a categorical variable. So categorical sex with two levels. Okay, and the columns are 4 levels of categorical color. Okay, so this is a 2x4 contingency table, 2 rows, 4 columns. Okay, and we are essentially trying to test for if we are essentially interested in identifying if there is any association between color of the coat and the dog's sex. Okay, so does a particular color of the dog means that they're also going to be of a particular, they're either going to be more females or males belonging to that color. So how do we test this? So the test essentially is, again, chi-square. The only thing that tries to is different is what our expectation is going to be. Okay, so in contingency tables, the expectation is again very simple to calculate. It essentially arises from the fact that how do you actually calculate the probability of something happening, given that you have seen the total number of such events. Okay, so the total number of males are 450, and the total number of blacks, uh, black dogs, are 328. Okay, so in an ideal world, or in a hypothetical world, to be more precise, what do we expect? So we expect that
the expectation for male and black. So what's the probability of being a male? That's 450 divided by 1000. Okay, there should not be any doubt there. So we have 450 males among total of 1000 males. So that's the probability of being a male. And then what's the the number of blacks are higher. So the number of blacks are 328. Okay, so you essentially are multiplying this value by the total number of males. The reason we are doing that is, or you can the other way to think about this is the probability of being a white dog is 328 divided by 1000, and there are 450 number of males, and hence this is kind of the expected number of black and males that you're going to see. Okay, is that clear? Any questions there? So that's a very simple and intuitive way to understand why we are doing this. So I cheated a bit and I put down all the values for this expectation here. Okay. And the only thing that you need to really figure out is how to actually calculate these values, but they're not difficult to calculate. And you don't really have to do it for all the values. So for example, if the moment I calculate what's the value for male, I can do so for the corresponding female by just subtracting the value for the corresponding row. Okay. And that's how I get my 180.4. Okay, so we get the expectation value. We can actually calculate how much the chi-square statistic is. So the only thing that's going to differ is how do you calculate your expected value, right? Everything else remains the same. Okay, and you can do this for the remaining 8 tabs. The chi-square value for this particular problem is around 4.7. But I actually went ahead. We did not solve a lot of previous problems. The first problem was asked us to calculate the state the null inwards. Okay, so the null hypothesis is there is no association between the coat color and sex of the dog. Okay, what is this null hypothesis in symbols? Okay, and a lot of people get confused about this point. So let's just think about it, right? So we're given two categorical variables. One is sex and one is coat. So if there is really no association, what does it really mean? So if you think about in terms of probability, if I'm looking for this conditional probability that the dog is male, so if I condition it on the fact that what color that particular dog is coming from, so let's do it for black, then there is no association between this and this, right? So there's no association between being a male and being a black colored dog. So in some sense, it's essentially also equivalent to being a male, but still being a different color. So that color could be gray. But that's again nothing special about the color. So it's also equivalent to being male and white. Okay. Or being a male, but being spotted. Okay. So in a sense, this is your null hypothesis. Okay. And this is just one way to write it. You can also think about doing the same thing for female condition on color. You can do the same thing. You can again write it in the form of having a particular color and being a female, okay, or having a particular color and being a male, and so on. Okay. So the kind of hypothesis that we are testing is kind of very strict. We are essentially making sure that all these probabilities are equal. So even if one of them is unequal, or even if one of them does not satisfy this, then we will reject the null. Okay. Okay. So part C is something which you should be able to solve. Question. Okay, let's see the question. Okay, good question. So P, does this work? Okay, so is P black, male? So, okay, let's write this down. So this is a continuation of this. So does this suffice, right? So this by itself is not sufficient. The reason this is by itself is not sufficient is because we have in a sense not calculated the probability. So it's not testing for association between all of them. Okay, so if you write it in this form, you'll have to write out the other three possibilities as well. And the other three possibilities are P white. So this needs to be a plus. Okay, so, and by plus I mean it's an and. So white male equal to white female and dot dot dot. That dot 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 essentially means that you need to do it for all colors. Okay, and there is an and here. Okay, so we move ahead and we were going to solve C. So in part C, we are asked what is the value of black probability of being a black given that you're male. Okay, so this by now should be very easy for you to solve. So we are black and we are male, but we are only males. Okay, so black given that you're male or given that the dog is male is that the dog is black and male divided by the probability that the dog is actually a male. So how do we get this? So very simple again. So what is the probability that you're black and male? So the black and male is, let me use colors. So we have 158 that you're a black and a male, and you are 450 total number of males. Okay, so this is equal to 158 divided by 450. Okay, so similarly, what's the probability that you're a male and you're spotted, given that you're spotted? So this is important. This is important because at this point you should not be doing any mistakes, and you can expect a problem of similar nature in the exam. Okay, so no issues there. The only thing that you have to really do is read the numbers from the table. So 150. So we are spotted and we are male. So spotted and male, that means we go this value, and spotted. Sorry, what's the spotted? So the reason we're spotted is 93. Okay, so this is 46 by 93. Okay, so just to be consistent. Okay, so nothing special there. We move on to problem D. So problem D is actually asking us to do the test of association. And what would our conclusion be? Oh, so sorry, problem D. Problem D is asking us to test the contingency tables degrees of freedom. Degrees of freedom are R minus 1 times C minus 1, which is number of rows minus 1, number of columns minus 1. So this is equal to 3. Okay, and problem E is asking us to do the t-test. So I already told you what the value for the chi-square statistic is. Okay, and the chi-square statistic is 4.7 with a degree of freedom 3. So we go back to our table. So a degree of 3, 4.7 happens to be somewhere between here. So this is 4.7. So P is between 0.2 and 0.1. Okay, this is again non-directional, and that's what we are working with in this domain. Sorry, so this P is essentially between, so we fail to reject the null. Okay, any questions about any of this? Okay, so we just have like 5 minutes to go over some of the review problems. And let's choose which problem we want to do. So let's take problem one. Problem one gives you two columns again. So you're essentially testing for difference between the two groups. And the first problem asks us you to calculate the standard error for the mean of the correlation surgery. So what's the standard error? So nothing special. It's just a revision of what you did for, sorry, is the standard deviation upon square root of n. So make sure you understand what the formula for the standard deviation is. It's already given in this particular problem, but it might not be. Okay, and the root n is your root 52 here. What about problem B? What is the standard error for difference in the two means? How do we calculate that? Any guesses? Anyone wants to take a guess at this? So you're given two surgeries. You're asked what is the standard error of the difference in the two means? How do we do that? Okay, that was quick. So 0.47. So how did we reach there? What would be the formula, first of all? So the formula is very simple, right? Right. Right. Yeah, sure. So I was actually asking the standard error of the difference. Okay, sure. Yes. So it's the standard error, summation of the standard errors. Okay. And the reason it's this is one thing that you should have noted in the beginning is this is an unpaired design. Why is it unpaired? There are two ways to look at it. And the first way is you'll not be given in the exam problem what design you're going to use, right? So it's very simple to see why this is an unpaired design. And in this case, the number of samples are different. That said, other way to think about this is you'll never do a surgery again on the same patient. So once you've done a conventional surgery, there makes no sense to actually do a coblation surgery on the same patient. And hence it has to be an unpaired design. Okay. Okay, so I'll skip C, D, and E. Maybe I'll talk about E. So E asks you to calculate the standard error, the effect size. So make sure you understand what the meaning of the effect size is. The effect size is asking you to calculate the different, the number of difference that you see having accounted for the standard error. Okay. So in some sense, it's measuring how much amount of difference that you see having adjusted for the amount of variation that you see in the data. Okay, I'll skip the rest of the things. Let's go to which test is more powerful. So obviously, Wilcoxon sign rank. Okay, and why so? Because you're using rank plus sign information. Okay, whereas sign only uses the sign information. What's the difference between Wilcoxon Man-Whitney and Wilcoxon sign rank sum? So this is simple. So this is just sign rank actually. So Wilcoxon sign rank is telling you you do this in a paired setting. And this you do this in an unpaired setting. Okay. When should Wilcoxon, so let's do problem 3. When should a Wilcoxon Man-Whitney test be preferred over the t-test? So you have either a very small sample size, okay, or both of these, the normality assumption is not satisfied. How will you check for normality? What's a quick check for normality? Yep, so we'll check for QQ plot, right? Okay, so QQ plot for a normal sample should look like all the points should lie on this straight line. Okay, so we're almost out of time. I would encourage you to do the rest of the tests, the rest of the problems. These are actually designed for you, but I just wanted to give you a quick overview. So I'll make the solutions available, so you'll have access to them. But before you look at the solutions, make sure you go through the problems. Oh yes, degrees of freedom for problem 1. Okay, that's a good question. So yeah, you'll always take the conservative approach. Okay, so DF, so just write down here in red. So DF, use conservative formula. Okay, just min of. Okay, this is for problem 1. Okay, I'll stick around for a while. If you have any questions, I'll take that. Otherwise, you're free to go. And good luck with your exam. Make sure you turn this on time. Okay, when you have 24 hours, you'll have access to all the resources. We expect you will not be collaborating with each other. So make sure you follow the honor system and you have access to all the notes and solutions for quizzes, homeworks, everything. And the exam is pretty easy, so it should not be a problem. Just make sure you turn this in time, okay? Okay, I'll stick around for a couple of more minutes. If there are any questions, I'll take that. Otherwise, you can email me if you have any questions. Let's see. Okay, so there's one question about how did we get the expected, let me make sure I get it right. So total for male. Okay, so for calculating the expected, how did we calculate the expected, right? So in order to calculate the expected value, so let's look at the total numbers. So the total number of males are 450. The total number of, or the total population is 450, okay? So what is the probability of being a male? Is 450 divided by 1000. Okay, so this is expected. So what is the number of spotted, let's say? So number of black. Okay, number of blacks are total of 328. So, okay, so the total number of black that are there in the population is 328. And each of them in some sense has this probability of being a male. Okay, so the total number of blacks are 328. The probability of each of them being a male is 450 by 1000. Okay, so these implies that the probability that I'm a male and I'm a black, sorry, the number actually, not the probability. The number of black and male is 328 divided by, multiplied by the probability that I'm a male, which is 450 divided by 1000, okay? You can do the same thing by working with the probability of being a black, which is 328 by 1000, and the number of males, which is 450. So there are 450 males, or let's do it for this problem. So their number of blacks is 328. And each of these 328 has this probability, 450 divided by 1000 of being a male. So what is the total number of expected black and males? That's simply the multiplication of the number times the probability. So this is, okay, how do we get this? This is your number, and this is your probability P. Okay, does that answer your question?
Okay, why is it not 158 by 1000? Okay, let's see. Okay, that's a great question. So 158 by 1000 is the probability of being a black and a male. Okay, so you ask actually a very good question, and the reason we don't work with the probabilities directly is because actually the chi-square test is specifically designed for, in some sense, it's actually designed for working with not with proportions, but with the actual numbers. Okay. And that's why we are looking at the expected number, not at the expected proportion. If we had been looking at the expected proportion, then the answer would have been slightly different. Actually, it would 158 by 1000 is also is not the problem. Okay, so let me write everything down because it will get confusion. Okay, so let's ask ourselves, why not 158 by 1000? Okay, so the reason for number one is we work with counts. Okay, we work with counts and not proportions. Okay, and the other way to see this is if there is no association between being a male and black, this is actually equivalent to being probability of being a male times probability of being a black. Okay, so you're right in some sense. So this number would have actually been this, right? So 450 by 1000, that's the probability of being a male. What's the probability of being a black? That's 328 divided by 1000. Okay, so one alternate way is what you would have done. So you would have said that how different is 158 by 1000, which is what you're observing, okay, minus this expected value, right? 450 by 1000 into 328 by 1000, square of this divided by 450 into 328 by 1000. Okay, so we generally keep ourselves working with the count data, and that's why we don't do this. Okay, otherwise it's a valid thing to do in principle. Okay, but we'll keep ourselves consistent and we'll keep working with the numbers. Okay, otherwise it's what it's saying is more or less a valid approach. Okay, does that answer your question? Oh, sorry, I'm so sorry, I forgot. Oh, I'm so sorry. Okay, sorry, let's do it again. Okay, I'm really sorry, I forgot to share my screen. Okay, so let's do it afresh. So what's the probability of being a male? So the probability of being a male is 450 by 1000. Okay, how did we reach there? So we reached there because 450 is your total, right? Actually, let me just do it from here. So the probability of being a male is 450 by 1000. The number of blacks is 328. So the probability of being, so the number of blacks who are males is given by the total number of blacks, which is 328, multiplied by the probability of each of them being a male, which is 450 by 1000. Okay. So we generally work with the numerical, what I was saying, and when I had not shared my screen, was we generally work with the numbers, and that's why we are calculating the expected number. There is, however, a valid other way to do this is to look at the proportions, but we don't use that approach. Okay, and what would happen if we were working with proportions? So you can imagine that if you're working with proportions, I mean, it eventually actually boils down to the same thing. So if you were working with proportions, then what is the probability of being a black and a male? If there is no association, that's essentially equal to being the multiplication of these two probabilities, right? Because these are in the null, they are assumed to be, this is assuming no association. So well, this is valid. You can do the same thing.
And if you do the same thing, you will essentially get the same value, right? You'll essentially, uh, the proportion for what you're seeing in terms of black and male, this is observed 158 by 1000. The expectation is 450 by 1000, which is the probability of being a male, multiplied by the probability of being a black, which is 328 by 1000. Okay. Divided by the expected, which is 458 into 328 divided by 1000. Okay. Now, what does this translate to? So this translates to this value. Still take the square. And this 1000 comes out. So this becomes 450 into 328. And this goes actually, so this still remains 1 by 1000. Okay, so the two approaches are very similar, but we will have an extra factor of 1000 featuring in there. Okay, that's the only difference between what we're going to do. But we work with the counts data, and that's why we're going to stick to this approach of actually calculating the numbers and not the proportions. Does that answer your question? Okay, cool. Okay, all right. Any other questions? Okay, cool. Good luck.